cosmos, we venture to the main asteroid belt, located between Mars and Jupiter. We will explore its structure and the unique characteristics of the objects within it. Discover the composition and distribution of the main types of asteroids and meet the largest bodies in the belt, including its sole dwarf planet. Learn more about potentially hazardous asteroids, and get familiar with meteoroids, bolides, meteors, and meteorites. We will also highlight the remarkable achievements of multiple space missions that have studied the small bodies in the solar system. Sit back, relax, and enjoy the show. Asteroids are small celestial bodies, remnants of the solar system's formation about 4.6 billion years ago. They are invisible to the naked eye and thus were unknown to humanity until the early 19th century. The first asteroid was discovered in 1801 by the Italian priest and astronomy professor Giuseppe Piazzi. Using a telescope at the Palermo Observatory, he noticed a star-like object, which he mistakenly identified as a comet. Ceres was detected between the orbits of Mars and Jupiter, at an average distance of about 414 million kilometers from the Sun. At that time, some scientists mistakenly believed an unknown planet could exist there. During the following years, a group of European astronomers conducted an extensive search in this part of the solar system and discovered three similar objects: Pallas, Juno, and Vesta. The English astronomer Sir William Herschel suggested that the bodies in question should be named asteroids, which means star-like in Greek. Over the next 60 years, objects identified in this region reached 100, while nowadays, their number is in the millions. They form an enormous structure called the main asteroid belt, which spans over 1.22 astronomical units. 1 astronomical unit is the average distance between the Earth and the Sun. The shape of the asteroid belt resembles a torus, whose volume increases towards its periphery. The objects within it move along elliptical orbits with an eccentricity of less than 0.4 and an inclination relative to the ecliptic that usually does not exceed 30 degrees. The asteroid belt formed in the protoplanetary disk around the young Sun in the early stages of the solar system. The mass of the available matter in that part of the disk was at least twice that of our planet. Under gravity, dust clumps began to grow to create ever larger bodies. Some reached sizes of tens or even hundreds of kilometers, called planetesimals and planetary embryos. None of those bodies managed to accrete enough matter to become a full-size planet. The main reason was the strong gravitational influence of Jupiter, which destabilized the orbits of many objects in the belt. During the initial 100 million years of the solar system's history, the main belt lost 99.9% of its primordial matter. Asteroids that remain to this day result from multiple collisions and mergers, leading to their current sizes and spatial configuration. Jupiter's gravitational field is also responsible for the large-scale structure of the asteroid belt. A process called mean motion resonance determines the boundaries of the belt. Repeated gravitational interaction arises when an asteroid's orbital period forms an integer fraction with the orbital period of Jupiter. Over time, that process is sufficient to perturb an asteroid to new orbital elements. 4-to-1 orbital resonance with Jupiter, at a radius of 2.06 astronomical units, can be considered an inner boundary of the asteroid belt. The outer edge of the belt, located at a distance of 3.28 astronomical units, is marked by a 2-to-1 resonance. Orbital resonance is also observed within the belt and is responsible for a lower concentration of objects in some areas, called Kirkwood gaps. The orbits of a small number of asteroids fall within the gaps at distances of 2.5 and 2.82 astronomical units, thus forming three zones: inner, middle, and outer belt. Each zone contains asteroids with different chemical compositions, divided into three main categories, denoted by the letters C, S, and M. About 75% of all observed asteroids belong to spectral type C, known as carbonaceous. They are redder in hue than the other asteroids and have a low reflectivity because of the high content of silicate rocks rich in carbon compounds. C-type asteroids dominate the asteroid belt's outer region, and in most cases, their structure is composed of many small spheres called chondrules. Those asteroids are some of the most ancient objects in our system, as they have not undergone melting or differentiation. During the formation of the asteroid belt, the temperature in the outer zone was low enough to allow the planetesimals to accrete water ice. The ratio of hydrogen isotopes in the outer zone of the belt is similar to their ratio in Earth's oceans. That suggests that at least some of the water on our planet came with asteroids and comets during the late heavy bombardment about 4 billion years ago. S-type or silicate-rich asteroids are more common toward the inner region of the asteroid belt. The spectra of their surfaces reveal the presence of silicates and some metals, but no significant carbonaceous compounds. They have a relatively high albedo, and form about 17% of the total asteroid population. S-type asteroids are much denser than the C-type as they have undergone at least partial melting and reformation. M-type or metal-rich asteroids account for about 8% of the total population and occupy the middle of the asteroid belt. They contain metals such as iron and nickel and fewer silicates. Those asteroids are much denser because of the exposure to high temperatures during their formation. S and M-type asteroids probably have formed from fragments of the mantles and the cores of destroyed planetary embryos. Within the belt exist sufficiently large bodies with differentiated internal structures. The largest one is Ceres, the only dwarf planet in the asteroid belt. Formed about 4.5 billion years ago, Ceres orbits 2.77 astronomical units from the Sun. The dwarf planet is considered a planetary embryo, unable to accrete more mass due to its proximity to Jupiter. It follows a low eccentricity orbit, inclined about 10 degrees to the ecliptic. Ceres is slightly flattened at the poles and has an equatorial diameter of approximately 950 kilometers. Despite its differentiated structure, no clear boundaries exist between the individual layers. Ceres holds more water than all water bodies on Earth combined, and its icy crust has high concentrations of minerals and salts. Evidence suggests Ceres may have experienced cryovolcanic activity in the past, as most of its craters are small and appear to be no older than a few 100 million years. The asteroid belt is home to three other large asteroids with diameters between 400 and 500 kilometers. Their names are Pallas, Vesta, and Hygiea, which are not considered dwarf planets. They are massive enough to have acquired a spherical shape and partially differentiated internal structures but have failed to clear their orbits of other bodies. Those three asteroids, along with the dwarf planet Ceres, contain about half the mass of the entire asteroid belt. Scientists assume that more than 200 asteroids larger than 100 kilometers have remained intact since the birth of the solar system. bodies over 1 kilometer in size are between 1 and 2 million, and even smaller ones are many times more. Despite the large number of objects in the asteroid belt, their combined mass equals only 3 to 4% of that of our Moon. Most asteroids have one or more small natural satellites, and the distances between individual asteroids range from several 100,000 to several million kilometers. About a third of all asteroids are members of so-called families, whose number exceeds 120. They include bodies that share common orbital characteristics and have similar compositions. Collisions between large asteroids in the past produced hundreds and even thousands of members of each family. Asteroids exceeding 10 kilometers collide relatively rarely, once every few million years. Bodies with sizes between 200 meters and 10 kilometers result from the accretion of many small fragments and thus have low density. The large amount of dust particles released during asteroid collisions contributes to the optical phenomenon known as zodiac light, which we will discuss in a future episode. Most numerous are the Trojans, centered around 2 points along Jupiter's orbit, known as Lagrange points. Asteroids remain there because of the equilibrium of their centrifugal force with the gravitational pull of the two massive bodies. Those Lagrange points form equilateral triangles with the planet and the Sun and are called L4 and L5. The Greek camp of Jupiter Trojans is leading the planet at L4, and those trailing behind at L5 comprise the Trojan camp. Both camps contain over 1 million bodies bigger than a kilometer. Other planets in the solar system also have Trojan asteroids, including Mars, Uranus, Neptune, and even Earth. A group of asteroids of particular interest are the so-called near-Earth asteroids, having orbits that bring them close to our planet. Some even cross Earth's orbit and are large enough to be categorized as potentially hazardous. Of the 35,000 known near-Earth asteroids, more than 2,000 could represent a threat to our planet in the future. Asteroids ranging in size from 30 microns to 1 meter are categorized as meteoroids due to their low hazardous potential. As they enter Earth's atmosphere, they are called meteors. Meteors with diameters less than a few centimeters burn entirely and are responsible for the optical phenomenon known as shooting stars. Large meteors, however, can survive their passage through the atmosphere and reach the surface. Upon entry, they appear as bright fireballs, visible even in daylight, called bolides. The remnants of these meteors fall to Earth as meteorites. Approximately 25 million meteoroids enter Earth's atmosphere daily, with a total annual mass estimated at 15,000 tons. Space exploration of asteroids began in 1972 with NASA's Pioneer 10 probe, which traversed the asteroid belt on its way to Jupiter. Over the following decades, numerous missions passed through the belt, including Pioneer 11, Voyager 1 and Voyager 2, Galileo, Cassini, Juno, and New Horizons. In 2000, the Near-Shoemaker spacecraft became the first to orbit an asteroid named Eros, and a year later made a successful landing. Japan Aerospace Exploration Agency, or JAXA, launched a similar mission called Hayabusa. The spacecraft landed on a small, potentially hazardous asteroid in 2005 and collected samples that arrived on Earth. In 2011, NASA's Dawn spacecraft reached the asteroid Vesta and after a year of investigation, set a course for Ceres. Dawn approached the dwarf planet in 2015 and conducted detailed research for nearly 3 years. In 2018, JAXA launched a second mission, Hayabusa 2, which deployed landers and rovers on the surface of the potentially hazardous asteroid Ryugu, and later sent samples back to Earth. NASA's analogous mission, OSIRIS-REx, was designed to collect material from 2 asteroids, including the 490-meter-wide Bennu. OSIRIS-REx gathered samples from Bennu in 2020, which were successfully returned to Earth 3 years later. Meanwhile, the spacecraft is heading towards the 370-meter asteroid Apophis, which will pass closer to our planet than satellites in geostationary orbit during its approach in 2029. The first spacecraft designed to deflect an asteroid from its orbit is NASA's DART mission. In 2022, the probe intentionally collided with a small asteroid called Dimorphos, which orbits a larger one named Didymos. The successful experiment showcased the feasibility of actively defending Earth from potentially hazardous asteroids. To date, 2 more spacecraft are on their way to asteroids, and 3 more will be launched in the coming years, as space exploration is vital to the survival of human civilization. Moreover, those small bodies represent an opportunity to look into the past and trace the evolution of the solar system. The asteroids may also hold the key to understanding the processes that favored the emergence of life on our small planet, in the vast cosmos.